Okay, here we're talking about the effective annual yield. This is the actual return on investment when compounding is taken into account over 1 year. Key there for an effective annual yield, time is always considered 1 year. All right. So when you look at a bank, like for an investment scenario, a lot of times you will be given essentially two interest rates. Okay. One is like the compound interest rate, and then the other is the effective yield. Think of the effective yield. It's the equivalent simple interest rate required to get the same amount of interest in the compounding scenario. And the effective yield is always a larger percentage, it should be, than the compounding. Okay? Because it takes, if you're only calculating the interest one time in a year, it takes a larger interest rate to gain that amount of interest from the compounding scenario. Okay? All right, so let's see this in action. You're investing P dollars into an account, 12% annual interest. How much would be in the account if you're, after 1 year, if you're compounded? Let's do it annually first. Okay, so if it's annually, you're not really compounding. Okay, we can treat N here as 1, I suppose. And we can say the amount after 1 year would be this P dollars times 1 plus our interest rate divided by 1 to the power of 1 times 1. Okay, now you simplify that. That would be P times 1.12 to the first power, or we're going to call that 1.12P. Okay, so the fact that P is being multiplied by 1.12 means I've got 12% interest here. As it should be, right? If we're doing this annually, the annual interest rate should be what we end up with. All right, now semi-annually, N would be 2 here. Okay, after 1 year, the amount in the account would be the principal times 1 plus 0.05 divided by 2 to the power of 2 times 1. Okay, now I can simplify that. I'm sorry, why am I putting 0.05 in there? This should be a point. I was confusing that with the last example. This should be a 0.12, shouldn't it? What I get trying to go from memory. All right, so that's going to give me P times 1.06 to the second power. And if I raise that 1.06 to the second power, I'll end up with 1.1236 times P. All right, so here I would say I end up with a 12.36% effective yield. All right, so we're saying that in order to get the same amount of interest in the semi-annual compounding scenario, I would have to use a 12.36% simple interest rate. Okay, that's what that means. All right, do it for quarterly. N is 4 here. A of 1 would equal P times 1 plus 0.12 divided by 4 to the power of 4 times 1, where that's P times 1.03 now to the fourth power. And that would be 1.1255 times P. So that's a 12.55% effective yield. Notice how this value keeps increasing. This percentage keeps increasing. We'll need a greater simple interest rate with a greater number of compounds at play. Okay. All right, and then the last one here, monthly, N would be 12 in that case. The amount in the account after 1 year would be your principal times 1 plus the interest rate divided by 12 now to the power of 12 times 1. Okay, that's going to be P times 1.01 to the 12th power, or that's 1.1268 roughly times P. So now the effective yield increases to 12.68%. All right, now example 5, we kind of take this a step further and actually apply this to some specific principal values. So here we got a $200 investment compounded daily. So that means N is 365 here, and it's yielding $220 at the end of 1 year. Okay, so we want to know what's the compound interest rate that would be used here. All right, so we can go back to this formula. Substitute in everything that I'm given. So my principal in this situation is the $200 investment. It's yielding $220. We'll take the 200, we'll multiply it by 1 plus the interest rate is our unknown, divided by 365 compounds, raised to the power 365 times 1. Because again, this is always over 1 year. Okay, so we got to solve this for R. I'm going to divide out 200. That's going to give me 1.1 is equal to the quantity 1 plus R over 365 to the power of 365. Now, I think I should take the 365th root of each side to clear that power. Okay, then to solve for R, a couple things I could do, different orders. Maybe I subtract 1, then multiply by 365. So that would mean R is equal to 365 times the quantity of the 365th root of 1.1 minus 1. All right, now that doesn't mean a whole lot to me in that form. So I'm going to approximate it. I did this ahead of time. 0.0953. So our interest rate being used here is 9.53%. Okay, so now we want to know what would the effective annual yield need to be in order to get that same amount of interest, to go from $200 to $220. That's what we mean when we say effective annual yield. So there's a couple ways you could go about this. You could go back to your regular exponential growth formula. Okay, the non-compounding one. And we could solve this for R. So 220 equals 200 times 1 plus R to the first power. Divide the 200 over, you'll get 1.1 is equal to 1 plus R. Subtract the 1, R equals 1/10 or 10%. Which I feel like most of us could probably have reasoned that out, right? If I'm going from $200 to $220, that's a 10% growth, right? Okay. So this would be the interest rate required in the non-compounding scenario, okay? Now, that's one way you could do this. Another way, this is kind of how I teach it in my regular pre-calc class. I use a simple interest formula. Interest is the principal times your interest rate. Okay? This is your simple interest formula. Well, think about, how do I calculate my interest in this case? I take the final amount, 220, subtracted by the initial amount. Yes, 200. And the initial amount is the principal, right? And then I always make T1 in this case. So look what I end up with. This is 20 equals 200R. Divide the 200 over. And I'm still going to end up with 0.1 or 10%. Okay.